a sub-list of that where the numbers go up, strictly go up. So one increasing subsequence would be 2, 3, 7. Those 2, 3, and 7 appear from left to right, and they go increasing. We're trying to find the longest increasing subsequence. And we decided last time that would be either 2, 3, 6,
sub-list of
9,
where the numbers go.
2, 3, 6, 7. Length 4. That's the best we can do for this example. All right, so we want an algorithm to take any list and report the length of the longest increasing subsequence. And eventually we'd like to pull that subsequence out. Okay, now first thing, it's an optimization problem. And no one knows of an efficient greedy solution. So what we got to do, or come up with for dynamic programming, is think of an exhaustive recursive solution. What often happens in a dynamic programming problem is you start with an initial problem, which is to find the length of the longest subsequence and of the list, and you've got to find a way of describing subproblems, and that can be a tricky thing. So what I'm doing here is, rather than try to define longest that takes a list as a parameter, we're going to define longest of I, where I is the starting point. So longest of I is the longest increasing subsequence that starts at index I. So what would be, for that array up there, that array just becomes sort of an implicit parameter. What's the longest increasing subsequence that starts at the last index? What's the length of the longest increasing subsequence that starts at index, whatever it is, 0, 1, 2, 3, 4, 5. Starts at index 7, the last index. 1. What about the length of the longest increasing subsequence that starts at index 6? Okay, 9. You're stuck getting 9, and then there's nothing bigger that follows. What about at index 5? 2, either 6, 9, or 6, 7. So this index here lets you describe a variety of subproblems. So we're going to come up with a recursive definition of longest of I. Now, once we come up with a definition of longest of I, how would we use that to solve our original problem? Not longest of 0. Longest of 0 would be the longest increasing subsequence that starts at index 0. Well, what is longest of 0? For this array up here. 3. You can go 5, or 5, 8, 9, or 5, 6, 7, or 5, 2, 5, 2, 6. There are lots of them, but they're only of length 3. So longest of 0 is not the solution to the overall problem. So if you have longest of I defined, how do you define longest in terms of it? Yeah?
It's the max of all longest.
It'd be the max of longest of I for all the i's. So if you had it solved, you would just iterate through the indices and find the I for which longest of I is the largest. Right? That's an easy part. Let's think about coming up with the recursive definition. So to motivate this idea, I have this array here. That's the array we're going to analyze in our example. These are indices into both of these arrays. This array is where we're going to store the solutions. So longest of 7 will go here. Longest of 6 will go here. Longest of 0 will go there. So we know a 1 should go there. The longest increasing subsequence that starts at index 7 is going to be a length 1. Okay? What about, let's say, this one here, longest of 3? What other solutions in this array? Imagine if this is partially filled in or fully filled in. What does this depend on? What other subproblems does this depend on? Yeah?
4, 5, 6, and 7.
Okay. You said it depends on 4, 5, 6, and 7. But let's make sure of that. We have an F stored here. So do we really care about what's longest of 4?
No.
Right? The idea is, if you start with F, C can't possibly be the next thing in the sequence.
Well, if it wasn't. Yeah.
Right, if it bit more to C, but for this example, we don't care about that C. We don't care about what's here. We don't even care about what's there.
It's only 6.
The only thing that matters is here. And in fact, so the longest increasing subsequence that starts at 3 is going to be 1 more than the longest increasing subsequence that starts at 6. So how could you characterize, if I point at any given place, which things to the right do we care about? Which subproblems do we care about? When do we care about longest of I if we're starting at 2?
For which A of I is greater.
Right, we care about indexes where this letter is greater than that letter. Okay? Now, having motivated it that way, let me put this up and see if it makes more sense than I did last time. This says that the longest increasing subsequence that starts at index I is 1 more than something. And that something is the max of a bunch of things. We'll come back to that. Let's just fill this out. We know the answer, if you're at the very end of the array, the answer is going to be 1. Okay? Now, to compute longest of 6, which entries in this array does 6 depend on? None of them, because j is bigger than everything to the right.
It's just 1.
So the answer there is going to be 1. Okay? What about 5? It depends on, it's interested in that. So it's possible to start with F and then go to J. So the idea is that what you write here is 1 more than the largest thing that sits under a yellow entry. So 1 more than that 1. So we'll put a 2 here, because we can go Fj. Now, what about that C? The next letter in the sequence could be Fj or E.
But the max is F.
So what we do, we say, okay, we could go, we could go CF or CJ or CE. What we do is we look and see, okay, which of those leads to the longest subsequence? That does. Add 1 to it, and that goes there. Whatever this sequence was, there's a sequence of length 2 that starts here. Since C is less than F, there's going to be a sequence of length 3 that starts here. Because we just go CF and then wherever F went to. So we fill that in. What about that entry there? FC is not going to work. FF is not going to work. Really, J is the only possibility. So the number we put here is 1 more than that. So we put a 2 there. Okay? H just depends on that J, so it's going to be 1 more than the entry under there. So we get the 2. B, on the other hand, we could go BH, BF, BC, all those things. So we just take the max in here, we add 1, and that's where the 4 comes from. And then E depends on all those things. So we take the max of 2, 2, 2, 1, add 1 to it, we get 3. So what we've done is we've just made a single pass and filled in that array from right to left, using that formula. Now back to the formula. What's that formula say? Yeah?
In the parentheses, is that a piecewise function?
Yes.
Okay.
So you can think of that as an if then else.
Okay.
The thing in parentheses, the value is going to be longest of j if a sub I is less than a sub j, and the value is going to be 0 otherwise. Right, so it's a piecewise function. So it's longest of I is 1 more than the max of some stuff. And the things that we look at, the stuff is characterized by this 1 less than j less than n. I less than j less than n. Yeah?
Could you also fill the array with 0 first and then go through and check?
Fill the array with zeros.
So the longest array, just fill it all with zeros and then work backwards?
Well, yeah, it doesn't really matter what you fill it with because we're working in this direction. We never look at an entry we haven't filled in first. Okay? So what's the importance of saying think of that like a summation. Instead of adding up everything as I goes for j between I and n, we're maxing everything between I and n. So I less than j less than n, I is fixed, n is fixed. That just means every index to the right of I. what's the deal with that piecewise function? Go ahead.
That's the part that says if the value is larger than our value. So
Okay.
the value of that index.
So it's saying, let's say j is 5. It's saying we care about this 2 only if this f is less than whatever stored at index I. I mean greater than.
So make sure it's increasing.
Right, so that's the part, that if up there is what makes sure the sequence is increasing. And if a sub I is not less than a sub j, the max is going to be looking at a 0. So if we go back, let's go back to here. It's not really working right. That's better. Go to here. Okay, so when we're computing what goes in this box, we find the max of that expression up there for every index from 1 to 7. Okay? So what will be the contribution of index? When j is 1, what will be the value of the thing in parentheses?
0.
It's not showing the... Okay. But the contribution of, when j is 1, it'll be 0, meaning otherwise. Okay, so that's 0. What about here?
That's going to be 2.
2. So the things that are highlighted yellow are the ones for which a sub I is less than a sub j. So we're taking the max of 0, 2, 2, 0, 2, 1, 0. And the max is 3, and we add 1 to get 4. So don't be snowed by the mathematical notation. It's essentially a summation, except for using a max instead of plus. In terms of programming, what is that? It's a loop. It's just an optimization loop. You're looping from I plus 1 to, you start j at I plus 1, you stop at n minus 1. And you're taking the max of longest of j, for assuming that a sub I is less than a sub j. And in fact, there it is. So here's longest increasing subsequence here. Let's look at this one here. It takes I as a parameter. It goes from j equals I plus 1, as long as that's less than a dot length, that's our n. If a sub I is less than a sub j, in other words, if the letters are the right order, max length is math.max of that length and longest of a and j. So that's just, that loop's computing the max. We've got the max, we have 1. Yeah.
But this doesn't give us some increasing subsequence. It gives us just the length of it. But
Right. This gives the length of the longest increasing subsequence.
Would we want the actual subsequence too? Or?
Yeah, we would like to be able to. It turns out if you can compute the length of the longest subsequence, it's easy to pull out the actual subsequence. In fact, if we go back here, let's just see how. We know the longest subsequence starts here, right? Because that's the biggest entry. So the longest increasing subsequence starts here. So that starts with a B. Now, where did this 4 come from? Why do we write a 4 right there?
3 plus 1.
Because 3 was the max that we cared about. So that means the next one is C. Why do we write this 3 right here? Because of F. And why do we write 2 right here? Because of B. Because of this.
Yeah.
So J. So generally, once you've done the calculation, you can easily reverse engineer it.
So this is quadratic time?
Yeah, this one is quadratic time. So that's the program. So this here is just the code form of that there. Okay? Now, sometimes you'll be, in this case we're interested in a max, sometimes you're interested in a min, sometimes you'd be interested in, say they're Boolean values, you'd be ORing things together, sometimes you'd be ANDing things together, it just depends on the problem. So that program right there, there's longest of I, and there's just plain old longest and it's just looping through, looking for the max. There are no arrays here. Notice back here I was using an array, just to motivate it. There are no arrays there. It's just making recursive calls. Things I was writing as arrays are just recursive method calls. So, what would be the complexity of that? Yeah?
N squared?
No.
Oh, no.
We can turn this into an n-squared algorithm. Yeah?
Oh, exponential?
It's exponential. All right, let's see what it does. You call longest of SS, it iterates I, it's iterating I backwards. And so it solves the problem for I equals 7 first. To solve I equals 7, it's got to solve the problem for I equals 6 and 5 and 4 and so on. Then it turns around and, so in solving the problem for, I got that wrong. It solves the problem for 7. Then it solves the problem for 6, and so on. But suppose when it's solving the problem for 6, or 5, or 4, this one is going to recursively solve the problem for bigger j's. You end up solving the same problems over and over and over again. And so that's why you end up with an exponential algorithm. So the idea behind dynamic programming is, first you write a simple recursive solution. You observe that there are only a polynomial number of different subproblems. How many different subproblems are there for an array of length n? The subproblems are the form longest of I. N. They're n indexes. So there are only n subproblems to solve. But this, if you actually try to run it, solves some of those subproblems over and over and over again. And that's really inefficient. And so the final step, the dynamic programming step, is to modify this so it only solves each problem once. Okay? And this is the idea. The simplest way to do it is once you have a recursive solution that works, you just create a cache that maps that parameter, basically it maps indexes to the longest subsequence that starts at that index. We call our helper with that cache. And what happens in the dynamic version is, when you are asked to compute the longest subsequence that starts at index I, first you look it up and see if you've previously computed the answer. If you have, you just return it. Otherwise, you compute it and save it before you return it. So you only have to do the computation once. Everything after that becomes a lookup. So, we go back to here. We did this by filling in an array. What's happening here? What's being filled in here? Yeah, the cache is being filled in. So an additional thing you can do is after you've written it recursively, you've written it in a cached form, a lot of times you'll look at it and you think, forget about the recursion. I could just, instead of using this hash table, I could just create an array containing the solutions and just fill it in from right to left and avoid recursive calls altogether. Either way, it's going to be an n-squared algorithm. But directly just iterating and filling in the table, in a lot of cases, is going to be more efficient. So, step one is to figure out, we went from defining longest to defining longest of I. So coming up with the subproblems, a way to characterize subproblems. Then you come up with a recursive solution. Then you make the solution more efficient by memoizing. And if you wish, you can dispense with recursion altogether and just fill in a table directly. The cool thing about the recursive solution is it figures out, to fill in a table, you got to figure out what order to do it in. Why wouldn't it work to fill in the table from right to left, from left to right? Why did I go backwards? Yeah.
So that when you're doing 4, you already have 5, 6, and 7 done.
Right. When I'm doing 4, depends on all these things. Any entry only depends on the things to its right. So we want to go backwards. It's like solving a DAG problem. You want to make sure that before you try to solve this problem, you've solved all these problems. So we go backwards in this case. The recursion, let's say we started the recursion right here. It would recursively solve all those problems, cache them before it produced the answer. So it solves all the problems once, caches their answer, and then they eventually get looked up. Yeah?
Did it forwards, wouldn't it do it about the same anyways, because it was fill in each values as it goes?
Yeah, well what happens is if you do it recursively, you'll end up recursively solving all these problems, and then this is the base case. So once you hit the base case and it starts returning, the cache gets filled in that direction. Okay, so there's a lot to chew on there, but I would say the hardest parts of dynamic programming is coming up with a recursive definition. Making it efficient after that is really straightforward. It's just coming up with the inspiration to how to describe the problem recursively. Yeah?
When you're going into the recursion, like, couldn't you say that B can't possibly go to J because J is so large that that there's no other letters coming after it, so there's only one step, and it's much better to look at, say, C instead of J, kind of prioritizing.
Yeah, well, you've got to look at you've got to compute a max, so you can end up looking at all the possibilities. You discard them, you might discard them early or not, but you have to look at all the possibilities. All right, before I look at another example, are there any other questions? Okay, this one is called minimum edit distance. And the idea is you've got two strings, and you want to find the minimum number of edits that will convert one string into another. And by edit, I mean you are allowed to delete a letter from R. You're trying to turn R into S. So you can delete a letter from R, you can insert a letter into R, or you can replace a letter in R with a different letter. So for example, what would be the minimum edit distance between snowy and sunny? How many edits does it take to convert snowy into sunny? 3. So what do we have to do? We could change this to a U, change that to an N, change that to an N. Okay? Is there another edit, another 3 edits that would do the change? Yeah?
Delete O and W and then insert U.
Well, yeah, we could, let's see, we could stick a U between the S and the N.
Yeah, convert one of them to
Convert O to an N and delete the W. Okay? So that's the one I have on the slide here. Can you think of applications for such an algorithm? When would you be interested in the minimum edit distance between 2 strings? Yeah? Autocorrect. Okay, so like autocorrect. Think of a spell checker that's got to suggest, it knows your word isn't in the dictionary, but it needs to find words that are close to it. So it's going to find words where the edit distance is small. Now, in that case, how do you decide what edits are allowed if you're a spell checker? Why would these be the edits? Or would these be the edits? Yeah?
You'd want to replace a letter if they accidentally typed a letter that they didn't mean to type.
Okay. So I'll just paraphrase what he said. You want the edits to correspond to mistakes that people tend to make when they're typing. And people tend to maybe type a character they didn't mean to. So that's like a replacement. Or I guess it's not just typing mistakes, it's spelling mistakes. The edit's got to characterize types of mistakes people make. Yeah?
Are we assuming R and S are the same length, or can they?
No, they don't. R and S don't have to be the same length. Yeah?
I mean, would you want to look at the distance between the letters on the keyboard to words that would...
That would, yeah, so that would be interesting. If edits, for typos, you'd be interested in letters that are near the one. You'd be more interested in letters that are near the one where you or that you're supposed to type. Okay? What else besides spell check? Yeah?
password guessers.
Okay, password guessers, so how would that work?
So most people have some word and then they just mutate it just slightly. So you want to guess if real
Okay,
close to it.
all right. So if you knew the name of someone's dog, then
Yeah, their dog, their birthday.
right. So you mutate it slightly and get potential passwords. Yeah.
Maybe encryption, kind of. It's the wrong word, but like replacing it so that the word becomes obscured.
So obfuscation.
Yeah.
Yeah, you can use it for like certain things in like beat speed.
Okay. What about in genetics?
Mutations.
So there, if you've got two sequences of DNA, if two sequences of DNA have a short edit distance, that means maybe they're related in the evolutionary tree, and their mutations would be edits to the AGTC in the DNA. I've used it before to try to compare programs for plagiarism detection.
You do it at diff.
Take two programs and see what the minimum edit distance is. And if there's just a few edits required to turn one into the other, then that's sort of an indicator that one was derived from the other. All right, so there are various applications for it. And it's an optimization problem, and can't think of a greedy problem, a greedy algorithm. So we got to get some inspiration for how to solve this thing by trying all the possibilities in some structured way. And so if I just gave you this problem and didn't work you through it, I know you'd have a hard time coming up with a solution, because I know I would. What we're going to do is focus on making the last characters agree. And so let me show you what I mean. I'm going to break R and S into 4 cases. So in case 1, R and S agree in their last letters. So R starts with some letters and S starts with some letters. It doesn't necessarily have to be 5 and 3. R could be, S could be longer, they could be the same length, they could have any number of characters. I'm just saying that they end with an A. So let's say someone gave you R and S and you observe they end with the same letter. How could you turn that into a simpler problem? How could you convert R and S so that you have a simpler problem? Yeah.
Just remove the last character.
Right. The last character is already matched, so let's remove them and solve the simpler problem of matching all but the first character of R with all but the first character of S. So if we let E be the edit distance between the first n letters of R and the first m letters of S, that's going to be the same thing as, assuming R is of length n and S is of length m. That's going to be the same as the edit distance between the first n-1 characters of R and the first n-1 characters of S. So that's how we're going to characterize subproblems with 2 integers. The number of characters of R that we want to consider, the number of characters of S that we want to consider. What if they end in different characters, which they do in all 3 of these cases? One strategy to make these things agree is to replace that A with a B. So if we replace that A with a B, what's the subproblem going to be? Let's say we've got to do something to make these last characters agree. One thing we can do is change that A to a B. Yeah?
Once you change the A to a B, you're in case 1 again, and it would just be the minimum edit distance plus 1.
Right. So what we're going to do is transform R by replacing that A with a B. And now we've got to compute the minimum edit distance between these n-1 question marks and these n-1 question marks. But we've already spent 1 edit. That's the difference between this case and that case. Up there, there's no edit necessarily because they already agree with an A. Down here, we do 1 edit to turn the A to a B. And now we reduce the problem to solving it for these question marks here. So we reduced it to the first n-1 characters, the first n-1 characters. Okay? Case 2, case 3 up there. R and S differ in that last character. Another thing we can do is a deletion. We can delete the A and hope that the question mark that's exposed matches the B. Okay? So how would you describe that using this notation? I mean, so what I'm going to do is delete the A, leaving R like that.
N comma N equals 1 plus.
Okay? So to solve this problem, the number of edits for that problem is 1 plus, so the 1 is for the deletion, plus, now we got to look at the first n minus 1 characters of R and all m characters of S. Okay? The first parameter is shorter because we've thrown away a character from R. We haven't changed S at all. And then finally, we could do an insertion. We could insert a B at the end here. So we could transform R like that. Now, what have we reduced up to?
1 plus case 1.
Okay? So we can take the B's off. So S has gotten shorter, right? But R is still the same length. So it's 1 edit plus E of n comma n minus 1. So we're still looking at all n characters of R, but only n minus 1 characters of S. Yeah?
So would you want to pick one of these based on what character comes before the last
Okay.
one's done?
All right, so basically he's asking, we got these 4 cases. First we have to convince ourselves that there's no other possibility. We got to do something with the last character, and there's nothing we can do other than, if they don't match, other than a replacement, a deletion, or an insertion. But how do you pick? So he's proposing maybe you pick by looking at the preceding character. Okay? That's a good question. Is there a way to look at the preceding character and decide which of these 3 cases to pick? If we could, that would be a greedy choice strategy. You just quickly look at the last 2 characters to figure out what to do. Turns out that for any such strategy you can propose, we can come up with a counterexample for it. So what does that mean in terms of how would you decide which of these to do? Yeah.
Maybe try to make them both the same length.
Well, you could do something that tends to make them the same length. Okay?
Well,
Yeah?
In case 2 and 3, you just do both of them and figure out whichever one is less.
Right. So we could try to think of greedy choices that lets us decide which of these 3 to do when the strings don't agree. But I'm just telling you, you're very unlikely to come up with a greedy choice that works. The best we know how to do is just to try all 3 possibilities and see which is best. So if the 2 strings agree on the last character, then it takes 1 recursive call to solve the problem. That's good. If they don't agree, we make 3 recursive calls, figure out which is less, and return it.
Those recursive calls make
But each of those make 3 recursive calls, and each of those makes 3 recursive calls. And so your recursion tree blows up, and you got an exponential algorithm, which is bad. But how many subproblems are there? Remember, a subproblem we're describing with a pair of integers.
so there's only n squared of those.
Well, yeah, how many different numbers could be right here? N, technically n plus 1, because it could be 0. If your initial string is of size n, then this entry here over the life algorithm could be anywhere from 0 to n. So that's n plus 1. N's close enough. Same thing here, it's m. So it's n times m. There are only n times m different possible subproblems. That's a polynomial. Okay, so you've got an exponential number of recursive calls, but only a polynomial number of different subproblems. That means you're solving some subproblems exponentially often. This is the candidate for dynamic programming. You could write the straightforward recursive program and then memorize it. And the memorization will succeed because there's a small number of distinct subproblems. And memorization prevents them from being solved over and over again. Yeah?
So if this was used for autocorrect, we're using a quadratic time algorithm for each word in the dictionary, or each word in the block of text?
Right, so if we're using for autocorrect, we have to take a word. If we wanted to compare it to every word in the dictionary, yeah, we'd be doing a quadratic, but the words are short length. But you'd be doing it for every word in the dictionary. So yeah, it may not be the best choice for that. Different data structure might help. Okay. Now, there are various ways we could describe the solution. But let's work on it here. Why does that make sense? E of 0, 0 is equal to 0. What's that saying? Yeah?
Empty strings match.
Empty strings always match. No edits required. Why does that make sense?
So you have to do a bunch of insertions.
Right, you got an empty string and you got a string of length m. And I'm saying it takes m edits to turn the empty string into the string of length m. Because you've got to do m insertions. Okay? Now what about the opposite case? E of n comma 0, what would that be? That would be n. Then you're doing n deletions to turn the first string into the second string. Okay? What's that say? You're looking at n characters of R and m characters of S. And the number of edits to turn this into that is the number of edits to turn the n-1 characters to the n-1 characters. But we only use that case if the strings agree in their last character. So that was that case. If they agree in the last character, you just shorten them each by 1. And this was the other case, where it says the edit distance from the first n characters to the first m characters of R, first m characters of S, is 1 more than the minimum of these 3 things. Now, let me pause. I mean, it's important to soak this definition in, so I'll let you soak it in for a minute and see if you have any questions about it. Yeah?
So in the case of E of nm, where it's n-1 and n-1, what if all of the characters, say, n-2 through and m-2 actually match? Wouldn't the edit distance just be 1? Did that make sense?
Okay, so tell me what string you're proposing.
So let's just say it's apple and apple but with a P on the end instead of an E.
Right.
Okay.
So the edit distance is 1.
So the edit distance would be 1. But here we're saying that, like, how do we know that say 0 through n-2 and 0 through m-2 don't already match?
We don't.
Okay.
We just know if you give me APPLE and APPLB, we got to do something about the E and the B before we worry about the rest of the string.
Sure.
So there are 3 things we could try. The right thing to try is to turn the E into a B. That's 1 edit. And you're left with APPL, APPL.
Okay.
And that'll
Okay.
be 0.
I see.
Now, the other things you try, if you try to just delete the E, leaving APPL and APPLB, that's not going to lead to the optimal solution. But you don't know in advance. You just try all 3 and see where you get.
Okay.
So it's brute force, but we're rescued by the dynamic programming trick. Any other questions? Yeah?
Can we insert a letter to the middle of the word?
Yes.
So will that count as 2 edits?
No, it's just you can insert to the middle. You can insert to the middle with 1 edit.
But like the letter part will just shift to.
Yeah. Yeah. That's fine. But we had to find a structured way of approaching the problem. So rather than considering all possible edits in all possible positions, I sort of asserted, you have to think about it to believe it, that it's enough to just look at edits at the end of the string. And that insertion in the middle would be several recursive calls down when you'd actually do the insertion. You would discover that. If all it takes an insertion into the middle, you'll find it a couple recursions down. Any other questions? Now, I have written using square brackets as opposed to parentheses, which you'd expect if these were method definitions. So you can imagine just having a method that said, if n and m are 0, return 0. Else, if you're in the second case, return m. Else, if you're in the third case, return n. Else, if r sub n-1 equals s sub n-1, return the result of that recursive call. Else, return 1 plus the minimum of these 2 recursive calls. And we could do that, and then we could memorize it. But what do the square brackets suggest? Yeah?
You have a cache that's n by n, and then you're just filling it in.
Yeah, it suggests that you can also view this, rather than viewing it as recursive calls, you can view it as the problem of filling in an array. So there's the array that we have to fill in. Okay? So we got snowy, we got sunny. N ranges from 0 to 5, which is the length of snowy. M ranges from S to Y, which is the length of sunny. And you can think of, say, this box right here is the edit distance between the first two characters of snowy and the first 0 characters of sunny. So suppose we succeeded in filling in the correct number in every box. Where would our answer appear?
Bottom left.
Yep,
The top right.
top right. Top right is edit distance of 5, 5. So think of this as being E. This array is E. And our problem is to fill the array in. Now, if we wrote it recursively and memoized it, we would be filling in essentially you'd be filling in the cache in some order, and you would find the eventual answer at a specific spot in the cache. If you think a little bit more about it, you realize you can dispense with the cache, dispense with the recursion, and just write code to fill in this array. Where should we start when we fill it in? Does it matter? Yeah.
Along the left edge and the bottom edge.
We got to start. So you can't. We got to start here and work our way toward that corner. Now let's see how it works. Take that one in the upper right corner. Which other squares does the one in the upper right corner? Forget about what particular strings are. No matter what this, what can you say? What squares in the upper right corner? What squares does the upper right corner depend on?
The 3 squares that are right next
The 3 adjacent squares. So it depends. So let's look here. It might just depend on the thing that's diagonally down from it, diagonally down to the left. Or it might depend on the one to its left, the one below it, and the one diagonally down to its left. That's in general true, that as long as, when we try to fill in a square, we've got to make sure we first fill in we've already filled in the thing to its left, the thing below it, and the thing diagonally below it. So that suggests starting at the bottom and working up. Would it work to start here and do this row, and then do the next row, and then the next row?
No.
Why not? Yeah. Check its dependencies.
It depends on the one on the left. You just put the bottom up.
Well, let's say we start here and we work across. Let's say we get to this square right there. Which ones does it depend on?
1, 1.
Right, so 2, 1 will depend on 2, 0, 1, 1, and 1, 0. Would they have all been filled in? If you're doing the rows from left to right, yeah, the row below would have been filled in. And the row, everything to the left in the current row would have been filled in. That's all you do. You never look up, you never look right. So we could fill it in by row. What about by column? What if we started at 0 and did the first column up, and then the second column up? That works as well, because you're always going to have the thing to the left, the thing below, and the thing diagonally below filled in. So you can work your way up to the corner. What if you're not clever enough to figure out the order in which to do this? Yeah?
Let recursion take care of that for you.
Right. You just write it recursively and set up a cache. And it discovers the right order to do things in. All right? So we'll fill in that thing next. Let's take a break, and then we'll fill it in. Okay, so let's take the strategy of filling in this table from, we'll do the rows from right to left, bottom to top. Essentially, think about it recursively. We're starting with the base cases and working our way up to the recursive cases. Because you've got to solve those. If we did do it recursively, it would recursively work its way down to the base cases and solve them first anyway. The first solution to go in the cache would be the base case. And well, let's just do this directly as a table. So we're turning snowy into sunny. That's 0. What will the rest of the bottom row look like? Which case will be in here?
N0, so it's just N.
E00?
Right, so this is the case where n is equal to 0. And so it'll just store 1, 2, 3, 4, 5, just like that. Okay? So that's one case. What would be stored in the left column?
N1.
Same deal. All right. So I sort of did those to start with. So now we're going to start filling it. Now we're going to do it left to right, top to bottom, bottom to top. I'm going to color some squares yellow. We don't have to do that. The yellow squares occur to cases where the letters agree. So you can see that, like, this is, we got an S at position 1 and an S at position 1, so that's colored yellow. Or we have an N at position 2 of this string and it ends at position 3 or 4 of that string. I'm coloring them yellow because I know from experience if I don't, I'll forget that that's the place where the characters are the same. But I'll just remind us that instead of being in this case, we're in that case. All right. So, right away we're going to fill in that first yellow, so we know we're in this case because the letters agree in that situation. So what do we write in that box?
1 or 0.
It just says you look diagonally down to the left, and whatever is there, you copy up. So we copy up to 0. Now the rest of the things on this row are going to be, are not yellows. There's no character agreement possible. So for each of them, what do we do geometrically? What's the geometric description? Yeah?
Take the minimum of the left diagonal and bottom.
Right. In this case, you look to the left, you look below, you look diagonally down to the left. You take the minimum of those 3 and add 1. And that's what you write in the box. So what will we write in the box? 1, because 0 is the min. Now we take the min of 1, 2, 3 and add 1. 2. We take the min of 2, 3, 4, 3, and 4. Okay? So imagine writing a program to do this. This would be a doubly nested loop that's just iterating across, looking at 3 things, computing the min, adding 1, writing it in. It'd be a very fast, very filled in very fast. Okay? Now in the next row, it's the same way. All the way across, we're looking at, in this case, 2, 1, and 0. We do an edit of 1. 1, 0, and 1. 1. 0 is the min, so we put a 1 there. 1, 1, 2. 2, 2, 3 would be a 3. 3, 3, 4. 4. Then the upper row, the next row, 3, 2, 1. The min is 2, is 1, so we add 2. Now we're in a yellow case.
1.
Letters agree, so we just take the thing diagonally down and copy it up. 1, 1, 2, that's a 2. 2, 2, 3 is a 3. 3, 3, 4 is a 4. Up there, 2, 3, 4, the min is 2. We're in a yellow case, so we just copy the 2 up. And then we go 2, 3, 4. And then we're up that row, we're going to go 4, 5, 4, 3. 2. 3.
Okay, 3, yeah.
Still 3. 4. And not 4, that's a yellow case.
Sure. 3.
So we copy the 3. Okay, and the last thing we write in the upper right-hand corner is the answer. Okay? So we've taken what would have been an exponential number of recursive calls and replaced it with, a doubly nested loop, so a quadratic algorithm.
So how do we find what edits we need to make?
Oh, okay, so he asked, how do you find out what the edits are? And we'll look at that in a minute. Now, what if we did write it recursively? Okay, let's see what it would look like. So we're asked to compute the minimum edit distance between 2 strings R and S. So we call our helper function, which takes R, N, S, and M, basically. So You're returning the result of the thing in the upper right-hand corner, essentially. And then here is the actual recursive function. And you see, this is just like the math. If n is 0, return m. If n is 0, return n. If the letters agree, make one recursive call. If the letters don't agree, make 3 recursive calls, take them in, add 1, return. So that's what you get. If you forget about the table, just write it recursively. And in this case, it's pretty easy to figure out the order in which you need to evaluate things. In other cases, sometimes it's actually kind of confusing, and it's nice to be able to fall back on this. Okay. What would it take to turn this into a cached computation? What would we have to change about this? Yeah?
Add a reference to a cache and make it a 2D array.
Well, basically we have to add the cache. We check on the way in, see if the answer's been computed, and we save on the way out. So to do it, we take our main function and we'll just have it we'll pass in an empty dictionary that maps pairs of integers to integers. So the pair of integers are the n and the m part, and the integer is the actual edit. And then we change this method like that. Right? We check first, see if we've already computed it. If so, return it. Otherwise, when we compute an answer, we cache it and then return it. I wrote this a little bit differently than I've written them in the past. But basically, you only do the computation if you haven't done it before. And you always save the result so you can look at it later. So without the caching, exponential. Because you've got 3 recursive calls. It keeps tripling the number of nodes at each level of the recursion tree. So that's bad. It's like 3 to the n in the worst case. With the cache, it's just n plus n times m. O of n times m. So the O of n times n entries made in the cache. And there's the iterative version, which is just doing what we did. It creates the table. It fills in the bottom row. It fills in the left column. So it deals with the base cases first. And then it just does the double loop. And either copies up the thing diagonally down, or figures out the min of the 3 things, adds 1, stores it, and returns. That's also quadratic. Yeah?
That's still taking quadratic memory. Can you just bring it back to like linear memory?
Okay? He says it takes quadratic time, clearly, but also takes quadratic memory because we've got to have that table. So we could be clever. How could we make it so that it only takes linear memory?
You only use the row you're on and row below.
Right, we only ever need the row we're on and the row below it. So you can imagine having 2 arrays. One array contains the row below. The other array contains the row you're using. As soon as you fill in the row you're using, that becomes the row below. And the other array becomes your new current row. And you fill it in again. So you could get by with 2 arrays of length n, or 2 arrays of length m if you went in the other direction. So it becomes linear instead of quadratic in memory. Still takes the same amount of time, but you don't have as much memory. And that could be important if you're doing, you're doing a really large problem. You don't, imagine 1,000 by 1,000. Rather than needing a million integers, you just need 1,000 or 2,000 integers to store your table. So there are always these things that, different ways you can, the choices you can make. What would be the comparison, you think, between the iterative solution and the cache solution? Which would be faster? Would that be faster? Would that be faster? Yeah?
I think the iterative would be faster.
Yeah, the iterative one would be faster because they're filling in the same number of entries in the tables. Well, that, in fact, it's not even strictly true. I can think of a case, so generally, iteratively filling in the table is going to be faster than recursively filling in the cache, even though you're putting in the same number of items. But there are cases where you don't do the same number of items. Who can think of a case where the recursion could blow recursive version would blow the iterative version out of the water.
You
Yeah.
have two words that are already the same, so you just look straight down.
Right.
at them.
Imagine 2,000 letter words that are exactly the same. Edit distance is 0. The recursive version is going to start in the upper right-hand corner, but it's only going to make recursive calls down the diagonal, because it's always in that case where it only makes one recursive call. So it's filling in the diagonal. The iterative version would stubbornly fill everything in, even though almost nothing it's doing matters. All that matters is the diagonal. So in that case, the recursion would win. Yeah?
Could we like hotwire the iterative version to take advantage of that best case?
Could we? I mean, sure, you can always, you know, have it check for the worst, check for that best case. But in most cases, that would just be making the thing slower.
Because every time you have that, you can just kind of skip.
Yeah. Okay, so now we're going to talk about how do you actually get the edits out. So this is just repeating what we just did. I got to skip ahead here. Okay. So we want to recover the solution. So say we fill the table already, either iteratively or recursively. What edit did we do to Snowy to reduce the problem? What edit did we do to Snow to reduce it to SNO? That was, we deleted the W off of Snow. So that was deleting R3. Okay? Why did we write a 2 right there? The highlighted 2, where did we write it? So there we were trying to turn SNO into SUNN. We wrote the 2 because there was a 1 diagonally down. So what edit did that correspond to? We're essentially replacing O with an N and then reducing the problem to matching SN to SUN. So that was a replacement. Now, why do we write the 1 right there?
N and N are the same.
Yeah, we're in that yellow case, so we just copy up. Why do we write that 1 right there? Because there was a 0 below it, we added 1. That corresponds to that corresponds to inversion. And finally, we wrote that 0 because we're in the yellow case, and we came from there. So it may not be crystal clear what I did, but essentially you can work backwards from the solution, and by figuring out why you wrote a particular number in a particular spot, you can figure out what edit that corresponds to. But there's another way. Suppose this causes you a headache. How could we add another array, let's say, and do it so we don't have to reverse engineer it? The reverse engineering is easier. Yeah.
Just say the ones that you've made. Change
Yeah.
it over.
So you could record when you write, you know, a number in a particular box. You could put something in a different array in the same spot that says why you did it, and then you could recover the edits that way. As long as you can go backwards from where you were to the beginning, you can recover the edits that you have to do. Okay. All right, we're going to look at another problem, but I'll stop here and see if there are any questions about this one before I spring one more on you. Yeah?
If we do want to recover what the solution is, we do need to use quadratic time, don't we? Is there a linear time, or a linear space way to do this?
Right, so he's saying that our trick of only using 2 one-dimensional arrays won't work if we're trying to recover the solution.
You recovered it step by step, the other way out you do.
Okay, so let me, something I was sort of going to skip over. Let's suppose that you wrote suppose you had a second array that contained the reason why you did some edit. We could write the complete history. So we would write in this box that we did a replacement. And then we could write in this box that we did a replacement followed by a replacement. In this box we could write replacement, replacement, replacement. What would be the problem with that? So that in the end, the upper box would contain the complete edit. What could go wrong there? these strings that, however you're representing the edit sequences become longer and longer as you get deeper into that array. So now it's taking lots of space just to store the edits. So sometimes that can kill you. You can end up having possibly an exponential number of characters to store all the edits, or to store a solution. I don't know if you wouldn't have an exponential number in this case, but you end up with a huge number. So that's why you want to make sure you store a constant amount of information per box. And then you have to go backwards and recover the information. Yeah.
Do you store references to other boxes?
Yes. You could have a box contain the edit that you made there plus a reference to the box you came from. That would make the backtracking easier. There are lots of tricks you can try. Yeah.
Never mind, I just talked under again.
Okay. But the idea is, as long as you're careful, recovering the solution doesn't make the algorithm any more complex. All right, here's our friend the knapsack problem. So this is about the third time we've seen it. And we've seen that example before. The idea is the thief has a backpack of a certain weight capacity. The thief can choose items A, B, and C to steal. They have weights and they have values. And we want to steal the thing with the most value that fits into the available space in the pack. And we've done these examples twice. We're going to look at two variations, with repetition, without repetition. With repetition means you can take as many A's as you want, as many B's as you want, as many C's as you want. Without repetition, there's only one of each. Okay? So let's look at it with repetition. What's the choice that you make each time? So you're the thief, you got a backpack. It's got some room left. What's your choice? Yeah?
Do we have a max weight at this point?
Our backpack has a capacity. The capacity may have been reduced because there's already stuff in it. So what do we choose? Yeah.
You want to take the thing with the most dollars per weight.
Well, you're trying to come up with a greedy solution. We already tried and failed a week or two ago. Yeah?
It's the most valuable thing.
Most valuable thing? Well, that's again a greedy choice, and one doesn't exist as far as we
You
know.
try putting each one in the bag and then seeing how much you get in, and the
Right.
next one, and you do the max. And
In this case, you've got 3 items to choose from. And the way we solve the problem is we say, okay, suppose I pick item A right now. What's the best I can do? Suppose I take item B, what's the best we can do? Suppose I take item C, what's the best we can do? We just try all the possibilities and see which leads to the best choice. Well, that's our choice each time. We've got to choose which item to take. So let's let K of W be the maximum possible value of loot if a backpack has remaining capacity W. So initially, when it's empty, the W is going to be the capacity of the backpack. If you've already put some stuff in the backpack, the capacity will be reduced correspondingly. What's K of 0? Well, let me first observe. This is all for the first step. I've said this several times. You've got to define something that characterizes subproblems. In this case, subproblem is different capacities left in the pack. What's K of 0? What's the maximum value you can steal if you can't carry anything? Right, 0, that's a base case. Okay? Here's the recursive case. What's the best you can do if you've got capacity W? Yeah?
Could you subtract each of those items and then take the max of the capacity that's remaining?
Okay? I think this is what you said. So what this says is, for each I, in our case, there are 3 I's to choose from, 1, 2, and 3. For each I, what's this right here? What's V of I?
The value of I.
That's the value. So we're saying, okay, suppose we take item 3. That'll be 13 plus, what's this going to be?
Whatever else we can fit in the bag.
Right. We take the capacity. Let's suppose W is 20. We would take 20, we would subtract the weight of an item 3, that's 7, so this would be 13. So one possibility is we take item 3, and that gives us 13 plus 13 for value, plus however much you can do with the remaining room in the pack. You try that for all i's, and whichever is the largest is the one that you do. You try all three possibilities. In each case, for each possibility, that's the value of the thing you're stealing. This is how much room is left after you steal that thing. And this is the best you can do with that amount of space left in your pack. You just take the max of all three, and that's the best you can do with weight W. What's this proviso right here for? That says W must be greater than or equal to capital W of I. Yeah?
Keep you from overfilling the bag.
Right, you can't take an item if it won't fit. So you can't, you know, if little w is 6, you can't consider item 3.
Why is it less than or equal to? Shouldn't it just be just greater than? Because.
What, this here?
Oh, okay. Yeah.
Okay? So now, suppose you've got a big table, a huge backpack. How many subproblems are there?
It's almost like the next one.
Yeah?
Depends on,
What does it depend on? What's the number of subproblems depend on?
it depends on if you can find an efficient way to prune a large number of the subproblems that you don't need to consider.
Well, let's not worry about pruning. Just how many distinct subproblems are there?
D would depend on the weight of each item.
No, it doesn't depend on the items at all. Okay? So, there's our function, K of W. So, yeah,
Is it just for however many you can carry? So if you can carry 20, then you have 20 subproblems.
right. If W is 20, you'll have 21 subproblems, 0 through 20. If W is 1,000,000, you'll have 1,000,001 subproblems. Okay? So the number of subproblems is determined by W. The table doesn't matter. And so, the problem of solving this is basically the problem of filling in an array again, a one-dimensional array. This is the best you can do with 0, this is the best you can do with 1, the best you can do with 2. If you were to do it iteratively, how would you do it?
You start from 11 and
Well,
you
what would this entry depend on? Could it depend on things to the right, or would it only depend on things to the left? Only things to the left. So if you filled in this table from left to right, anytime you went to compute something, it would already been, the things it depends on would already been computed. So it's sort of like a DAG again. The subproblems form a DAG. The dependency between subproblems forms a DAG. And you just want to do it in the right order. So we'll stop there, and we'll continue with this next time.